Last time we started section 3.1, we were looking at numeration systems, and we had done Egyptians, Babylonians, and Mayans. And we were just on the verge of starting to talk about the Romans. We talked briefly about the fact that Roman numerals are still common today. We see them used in literature sometimes. We see them used on outline forms. We'll see them used on clocks. When we're dating things like sometimes like the Super Bowl and such like that. You'll also see them used on buildings if you go to certain parts of the country. So if you go to the East Coast, I had a brother-in-law who got married in the Washington, D.C. area, and the building that they got married in, the church, actually had an established date on it, and it was written in Roman numerals. So these are the basic Roman numerals, and you probably know, at least pretty far down, what their values are. So somebody tell me, what is the first one? Yeah, it's 1. How about the V? That one's 5. An X? 10. All right, so once we get past that, you've pretty much run out of your outlines because, right, your outlines aren't going much past that. How about an L? That one's 50. Good. Anybody know what the C is? It's 100. Hopefully you're noticing a pattern by this point in our numbers that I'm writing down. Even if you don't know what the D is, you can probably make a pretty good educated guess that it is 500, and an M is 1,000. Hopefully you're asking yourself a question like, well, what if it's bigger than 1,000? I mean, we've kind of asked ourselves that same question when we've had some of the other numeration systems. What about really big numbers? There is a way to deal with really big numbers. We didn't have to deal with that in most scenarios that use Roman numerals, but they do have a way to deal with it, so we'll talk about that. They also have a very interesting subtraction property that I'm sure you're aware of, at least with their smaller values. This is the subtraction property. We'll start with it first. To avoid repeating a symbol more than 3 times, we take a smaller value and we place it in front of a larger one. Now there are some conditions upon the ways in which we can do that. We're doing what they did, okay, so we don't get to do it the way we want to. That's not an option. We do it the way they did it. It's only one value smaller that may go before a value that's larger. In particular, it only works or is only effective or used when we would have our numerals 4 or 9 involved. So if we had the number 49, we'd be using this property twice, once for the 4, once for the 9. But if we had 48, we'd only be using it once for the 40 part. So I've got an example. We're going to write the number 90 first. Okay, so if we were writing the number 90, somehow in theory we could write down an L and then 4 X's, and that should be the number 90, right? 50 and then 40 more. In their system, though, they would never have written a numeral more than 3 times in a row. So we wouldn't have written 4 of the 10s. It's just not what was done. So instead, what they would do is that they would write the 10 in front of the symbol for 100, which is C. So you'd get, in essence, a 10 here, a 100 here, and because the 10 comes in front of the 100, there's a subtraction property going on. That number would then be 90. Now there's a caveat. We can't, like, it would be really nice if we could do the number 99 as an I and then a C, right? 100 minus 1. And that sounds like great. And next time you invent your own numeration system, you're welcome to do that. That's not what they did, though. They treated each of those 9s as separate values. In other words, how do we get 90? Well, we just did that. We do XC. 90 is because we have XC. And then how do we get 9? Well, that one you probably actually have seen and know. What's 9? IX. IX. There's a 1 in front of a 10, so that gives me 9 at the end. I know it'd be better to write IC. It'd be shorter, right? Yeah, but you can't do that. All right? Can't do it. So here's a good time to stop and ask you, who remembered to look at the Rayleigh Chapel clock? Did anybody notice anything about the Rayleigh Chapel clock? We hadn't actually talked about Roman numerals yet, but does anybody notice anything weird based on what I've said thus far about the Rayleigh Chapel clock? What's wrong? The 4. How did they write the 4? They write 4 1s. And you might say, okay, that's totally fine. You can write it that way, but do they write the 9 in a fashion like that? No, they don't. You'll see that on clocks sometimes. When the conventions of the actual system they're using, they just don't hold to them and they do something different. So that actually is an incorrect use of the Roman numeral system on our clock on campus. Let me show you what we do with large numbers now. There's a multiplication property. If we have a bar on top, kind of like, a line segment bar, like you use in geometry, if you put a bar on top of a numeral, a Roman numeral, it multiplies the value, whatever that would have been, by 1,000. And if you put 2 bars, like double bar, on top, it multiplies it by 1,000,000. So let's take a look at how we would write, for instance, 9,000. All right, so in many regards, we can kind of ignore the fact that there's 1,000 at the end. The 1,000 at the end is going to be taken care of by putting a bar on top of what comes before it. So what I really need to know is, how do I write a 9? So how do I write a 9? We already did it, right? Yeah, IX. And then the way that we turn the 9 into a 9,000 is we put a bar on top of it. That's the number 9,000. Now, let's say, just for the sake of argument, we had 9,432, something else. And it wasn't just 9,000. You'd still treat them very much like there's a break here, because the only way to get 9,000 and not to have to write lots of numerals, right, a V and a bunch of I's or something, or a bunch of M's, or the only way to do it is to still do the 9, which is IX, and put the bar on it to get 1,000. And then you deal with the 432. I don't mean to underline that like there's double bars there. That was a bad idea. You deal with the 432 as a separate value that's right beside it. So how do I get 400? You need a 500, and then you need a C in front of it to make it 400. So you'd get C and then D, because it's a 100 followed by a 500, which gives me 400. How would I get 30? 3 X's, and then I would have 2 giving me 2 I's, right? So it's totally fine to have a bar over part of the number and not over the whole number as well. Okay, the bar doesn't have to be over everything. Occasionally I have someone want to know what happens if I have the number 3,432. What do I do about the 3,000? Well, I don't need any bars. Why not? I can do 3 M's, and that would be the appropriate response. If there's no need for a bar, we're not going to use it. We're only going to use it if it's absolutely necessary. And then we'd have the 432 the same as before, CD, and then XXX and II. Okay? Any questions about that? Okay. Let's take a look then at a specific Roman numeral. Okay, so this Roman numeral is MCMX. And the first question, as it has been with all the other numeration systems, is what would have come before MCMX? And we always answer that by looking at what comes at the end of the value. So what is the ending value here? It's a 10. And if I were to decrease that by 1, I would get a 9. So the beginning, just like again on the other ones, doesn't change. It's MCM. Okay? And then what would I have to change the X to? IX, because that's how I get a 9 for Roman numerals. Okay, so we could pretty quickly move into what we get for the number afterward. What would come after MCMX? Yeah, an I. MCMXI. That would be our next numeral, just tacking on an I at the end. And then we're going to change this into our numeral, okay, the original MCMX. Okay, so M is worth 1,000. C is worth 100. And the 100's coming before another 1,000. So what does that mean? Yeah, this piece right here is going to be 900. The piece at the beginning is 1,000. And then what's the X at the end? 10. So what is the total after I take all that into consideration? 1,910, which looks a lot like a year. It could potentially be on a building. All right, and we're going to go the other direction. We have our number, 1,492,000. 19. Now, we know from what I've already said before that we're going to break it apart here, and we're going to deal with the value that's before the thousands comma, basically, separate from the one that's afterwards. Because this is a 1, that'll work. Because this is a 1 right here, I can actually treat this like it's the number 1,492 because I have a way to get a number 1,000, right? How do I get 1,000? An M, okay? If the number, the 1 at the beginning right there, had been a 4, we'd have a problem. I don't have for 4,000 because I can't write 4 M's. So if I had had a, I'll do it in a minute, but we'll see how it would have looked different if I had 4,492,019. Okay, so I'm going to do that one next just so that you can see the difference, because there is a difference if there's a 4 there as opposed to a 1, 2, or 3. So let's deal with it as 1, right? This is the number like the number 1,492. How do I get a 1,000? An M. How do I get a 400? I did it just a minute ago. CD, good. How do I get a 90? IX, good. And how do I get a 2? 2 I's. And this number is actually times 1,000, right? I mean, that's where I put that yellow line to sort of distinguish the difference. So all of that has a single bar over it. Yes, ma'am? Oh, 90. I said it wrong. You are so right. Thank you, Emily. Not 90. What is 90? We haven't done 90. That's probably why I was thinking about the other one already. We did 90, actually. XC. We did that one just a couple slides ago. XC. Thank you very much. If I'd looked at my notes, I would have seen it as well, but I didn't. And then I've got my 2 I's. Did everybody get that fixed? Thank you. Okay. And then I have, after the number that's sort of in the thousands place, I have the number 19. How do I get the number 19? Well, how do I get the number 1 in the tens place? An X, right? This is a 10. And then I have 9 ones, or 9. IX. So it's XIX at the end. I sort of made it look like there was a space there. That doesn't really need to look like that. You do need to be careful that the bars go over what you intend them to go over and don't go over extra, that kind of thing. All right, so let's see what would have happened differently if the number had been 4 million instead of 1 million. Well, we already said that we have to sort of draw this line right here. But the reality is we need a line right here as well. And we would treat this as though it was the number 4. So how do I draw the number 4? IV. And then to make it 4 million, I'd put 2 bars on top of it. The 492, we won't belabor the point too much. It was CD, X, C, and then double I. And that was in the thousands place, so there's 1 bar. And then I have the 19 at the end, which was XIX. So can you have a double bar, a single bar, or no bar? Absolutely you can.
Why is the 1 million not a double bar on the first one?
Because it's already 1,000 times 1,000. That's what you would get the 1 million to be. Yeah. Good question. Any other questions? Yes, ma'am.
Could we have written it, the M with 2 and then just the rest with 1?
So, like the way we think about mathematics logically, we think we can. But we also think that we should be able to write this right here, IC. And we can't for the number 99. We just don't. That's not how they did it. So to answer your question, historically speaking, no, you can't, because that's not what would have been done. Does that make sense? Mm-hmm. Yeah. Don't do that. Okay. I meant to bring my manipulatives, and I totally forgot, so I'll try to remember to bring them next time. We're going to think a little bit about base 10 blocks. You've seen these used, I'm sure, if you've been in elementary schools, kindergarten, pre-K, first grade, maybe even enough. Base 10 blocks do a really, really nice job of showing kids why you can and can't add certain sizes of things together. In some sense, why is 20 plus 5 25 instead of like 70? Why do I not add the 2 and the 5 somehow? And manipulatives do a really good job of showing that because they have different sizes. So let me show you what they would look like sort of in a written form if you were like looking in a textbook. A unit looks like a small square. A long is actually like 10 of those put together, and so it just looks like a long piece. A flat is a 10 by 10, so it's like 10 longs put together, and it looks like a big square. And then a block looks like that same big square, but it's three-dimensionalized. So you take your block and then you add, you know, the ending pieces together to try, and I'm not going to get it quite right, but that's not too bad. All right, pretend like that looks like a box. I kind of chopped it off on the side, but it's three-dimensional, okay? Now, when we think about doing it, you know, we're using base 10 because we do base 10. I mean, that's what we do our Hindu Arabic numeration systems in. But there's nothing super special about base 10. We could have done these blocks, these base 10 blocks, in another base system. We just wouldn't have them 10 long. We'd have them 8 long if we didn't have thumbs, right? No thumbs, we've got a base 8 system, then we'd have an 8 long, and it'd be an 8 by 8 flat and an 8 by 8 by 8 block or cube there at the end, okay? So there's nothing special about 10s, it's just that that's what we were accustomed to using. So if we had a base 8, I thought I was picking one that I didn't write down. This is what happens when I'm not looking at my notes very carefully. Okay. If we did have a base 8, how much would a unit, a long, and a flat be? Well, a unit is always worth 1. It doesn't matter what base you're in. And I already said it before, but does anybody remember? If I did a base 8 long, what would it be? It'd be 8 long. And if I did a base 8 flat, what would it be? 64. It's 8 times 8, or 8 squared, which is 64. And if I did a block, I wanted to call it a cube. If I did a block, an 8 by 8 by 8 block, or it'd be 8 cubed. Does anybody know what 8 cubed is? I should have offered bonus points if you did. No, it's 512. 512. So if we looked at this one on part B, it says considering manipulatives, how many units would 237 base 8 be? Well, if you want to think about it in sort of words, you'd have 2 flats, you'd have 3 longs, and you'd have 7 units, right? I mean, that's what you'd really have if you took the manipulatives and you put them in piles. That's what they'd look like. But how big, how many units is a flat in base 8? 64. So you'd really have like 2 times 64. And how many units is a long? It's 8 in base 8. And then how many units is a unit? Well, that's 1, right? It means 1. So if you grab your calculator and you multiply 2 times 64 plus 24 plus 7, what would you get? Somebody said it. What was it? 159 is correct. Good job. It'd be 159. Now, sometimes you'll see these blocks actually not stuck together. You can buy them that way, where the kids actually make them themselves. So they put 10 of the little units together and they snap together, like Legos, right? They're like Legos, but they're supposed to be used in school instead of not supposed to be used in school, like that, right? So you put 10 of them together and that makes your long. So like, if this is the idea, is if you had the ability to take these blocks, like we've just described, and break them all down, and all of a sudden now in your hand you have all the little bitty units. How many little bitty units would you have? And you'd have 159. That's what we're doing, is we're breaking them all into their smallest components. Note that this question that we just answered in part B is equivalent to asking what the number 237 base 8 would be if you wrote it as a base 10 number. So if I broke apart all those blocks and then I reassembled them into a flat that's a size 100 and longs that were size 10 and units that are size 1, what would I get? Well, I'd have 1 flat and I'd have 5 longs, and I'd have 9 units in our base 10 system. That's what would happen. So we're going to take a look at some other base systems, not numeration systems, but these are other base systems or other number systems. Base 3. We talked about last time that our base 10 number system had 10 numerals, but there is no numeral 10. There's a number 10, but it's 2 numerals, 0 and 1, right? So if you have a base 3 system, how many symbols do you think you have? 3. Yeah, I'm not trying to trick you, I promise. It's just 3. There's 3 symbols. What do you think the first one is? 0. Which means the next one should be 1. And then 2, and you're out of numerals. Because you said there's 3, and you were right. There are only 3, and I've written down 3 numerals. So once I get to the end of the numerals, I have to have a 2-digit number now. All right, that's what happens when we hit 9, right? When we hit 9, and this is something happened to my son. He went from age 9 to his birthday, and he became age 10, which is double digits, 1, 0. And that happens in base 3 and every other base as well. When you run out of numerals, you have to move into a 2-digit number, and the 2-digit number that would come after the 2 is 1, 0. I'm not going to say 10 because that inherently means we're working somehow in base 10. So I'm going to say the numerals 1, 0. What would come after 1, 0? 1, 1. What would be next? 1, 2. And then what do you notice? That's it. So what would happen once I hit equivalently like 19 in our number system? What would we do? Yeah, we increase the digit that's in the tens place. So here we're going to increase the 2-digit number's first digit. So this would be 2, 0, 2, 1, 2, 2. We're not going to do this forever. We're going to do one more. What happens when I get to 2, 2? That's it for all 2-digit numbers. There are no more 2-digit numbers in base 3. What would come next? There's no 3s. 1, 0, 0. A 3-digit number. Maybe that's what you meant. You'd have to have 3 digits. Yeah, you would. Good job. And then we'd keep going the process, right? And we go 1, 0, 0, 1, 0, 1, 1, 0, 2, and we'd run out of digits, and we'd have to do it again. Okay? So this process continues, of course, indefinitely. What do you think we're going to have when we have base 7? What are my numerals? 0 through 6. And what would come after 6 in base 7? 1, 0. Yeah. And then 1, 1, all the way up to 1, 6, and then I would get 2, 0, and we would continue the process. Okay, so how are the first 2 examples on this slide different than the last one? The number 12 is already a 2-digit number in our base system. Yeah, so in some sense, the first 2 examples I gave you are smaller than base 10, right? They have fewer numerals, whereas base 12 is bigger. It should have more numerals than base 10. So I need, how many numerals do you suppose I need in base 12? How many numerals do I need in base 3? How many do I need in base 7? So how many do I need in base 12? 12. I think you guys know the answers. You're just toying with me today. All right, so we're going to start at 0, and we're going to go up to all of our digits that we have, which is 9. I mean, we run out when we get to 9, right? So 1, 2, 3, 4, 5, 6, 7, 8, and 9. And we can't write down 10 because that's a 2-numeral number. We need another numeral, like a single value to write in. So I'm going to show you what your book does. I'm not super fond of it. I will tell you that right now. There's another book that we teach out of sometimes, not this class, but a different class, and I like what they do better. So let me tell you what the other book does better. They use the letters of the alphabet in order. So they go A, B, C, however many of them you need. This book uses T for 10, E for 11, and that's enough for us now. But if they went to 12, they would use W. And they don't have any other examples of what they use next. So I find that to be a very limiting way of describing it, but I don't want you to try to look at the book and see that I'm doing something different and confuse everybody. And that's my goal is not to confuse, okay? So T and E would come next. So T is 10. You might write yourself down in the word 10. Don't write down 10 because we're trying to avoid that. And this is 11. Okay, T for 10, E for 11. Now, at the point when I have the E for 11, that's 12 numerals, right? 0 to E is 12 numerals. What would come after E? 1 0 would, you bet. And I would go up to 1 9, just like I always would have. And what do you think would come after 1 9? Somebody said it. Not yet. Not quite. 1 T, 1 E, because those are the next numerals, and then I'd have 2 0, and we would continue. So once I hit 9, I go to whatever that is next one with the E and T, and then whatever is next with the E. All right. So kind of like what we did with the numeration systems, I want to look at what happens when we look for a number before and a number after a numeral in a different system. So here's an example. Number 10, find the numeral preceding. What does preceding mean? Before. And succeeding, which means after. So the number before, the number after each value. Okay? So what would, and I mean, I'm going to tell you, like, I obviously picked numbers on purpose here. That means one of them is going to be hard to do, okay? Because I want you to see what they are. The easy one here is the number before. What comes before 1 4? What is it? 1 3. It doesn't even matter what system I'm in as long as I have enough digits. Before 1 4 is 1 3, and this is base 5. So I'm going to write the numbers like they're in order. 1 3 base 5, 1 4 base 5. What would come after 1 4? It'd be 2 0. So, Erica, why would it not be 1 5?
Because you only have the numerals 0, 1, 2, 3, 4.
Yeah. There are no 5s or bigger in base 5. 4 is my biggest value. So I can't keep going in my numeration system. I have to, in some sense, sort of carry or round or move up. So the next one would be a 2 0 base 5. Okay, so T00 is in base 12 now. So the number they're giving me, if you will, is my middle number. The number after on this one's the easy one. What would come after T00? What is it? Nope. T01. You always change the last digit, remember? Right, what would come after 100? Well, 101. What would come after 900? 901. Okay, so it just changes the last digit. So T01 would be my next digit after that. That's the one that's easier to think about. The one that's harder to think about is the one that comes before. And the same is true for us if we think about the number 900. Now, you guys think about 900 and you know what comes before it because you've worked with math long enough that you know how your number system works. But if you literally were working with a child and you told them to subtract, 900 minus 1 is not the easiest subtraction number in the world, problem in the world. It's just not. Why not? What makes this challenging? What were you going to say? Yeah, those zeros. There's nothing to actually just do the subtraction. I have to keep borrowing or regrouping is that's like their catchphrase in all my kids' stuff right now. It's regrouping. We want to regroup. So they have to keep regrouping things, right? So that's basically what we're doing here too. We're doing T00 minus 1, and we're going to have to regroup if we think about it as a minus 1 kind of problem. So let's do it as a minus 1 kind of problem and see what happens. And then I'll talk with you about another way to think about it as well, and then you can pick whichever one makes the most sense to you. So if I do regrouping, if I do borrowing, the T needs to go down by 1. So what does the T become? A 9. 9 is what comes before T. But when I borrow or when I regroup, that means 12 numbers get moved over to the other slot, right? That's what we normally do, right? We usually move a 10 over because we're working in base 10. So there's actually a T here now, because that's 12. It's now in that slot, right? This is what you would do here, right? This 9 would become an 8, and there'd be a 10 here. Yes? Wait, what do we have? Are we in base? Oh, no, it would be an E, actually.
Okay.
I wrote it wrong. No, it would be a T. No, it would be a, well, it's this is what it is. Let me fix these parts right here. It's a 1, 0, but 1, 0 in our system is equal to the number 12.
Okay.
12 is what I wanted to write, but I was writing it as a T. Yeah, 12 is what we have there. And then I have to borrow from the 12, because I'm in base 12, right, to get this to move over. So this 12 becomes an 11. Now I can write a single digit E. And I have 12 left here. And I can actually subtract something, finally. So in the ones column or the units column, I have 12 minus 1, and 12 minus 1 would be 11, which is an E. There's an E here that I'm bringing down, and a 9. So this is 9, E, E. Base 12. One of the things I wanted you to see here is that conceptually that process is not as straightforward as you thought that it was when I asked you to do this, right? 900 minus 1, no problem, it's 899. Y'all did not have a problem thinking about that, and you probably thought about it within a second about what I said it, right? But your kids in your class, and maybe you too, probably wouldn't think about it as subtraction of 1, at least eventually. You'd probably think about it more like counting backwards, or what came before this, right? What comes before 900? Well, 899. So how do I think about that in maybe a more straightforward way? Well, let's take the T00. For wanting to find out what comes before, well, the biggest number will be where the zeros are. So what's the biggest number in base 12? E. 11 is, which is an E, you bet. So this one becomes an E, and this 0 also becomes an E. It's the biggest number. And I have to decrease my T by 1, and what comes before T? A 9. So it's 9EE. That's really probably closer to how your kids eventually think about it, not as subtraction, but as counting backwards. All right, what we're going to do next, instead of looking at numbers before and afterwards, is actually learning to convert numbers between systems. So the first way in which we're going to do is to convert whatever the base is. There's a blank here on purpose. We're not filling in the blank. Converting base blank into a base 10. And the way that we do that is that we put the numerals into expanded form. In a very real sense, we're going to do what I did right here. We're going to write out 2 flats, 3 longs, 7 units. That's how we're going to think about it. Okay? And then we're going to multiply the expanded form out, which is exactly what we did below that. 2 times 64, 3 times 8, 7 times 1. Add them up, and we're done. So we should see an example of this. In particular, what we're going to do is we're going to have each of the numerals that's given to me times a number. Now, the parentheses that I put in are going to be the powers of whatever base you're working in. So what is the base I'm working in on this particular problem? It's base 2. So in base 2, all the powers are 2's. Now, the first one's always 1. It's 2 to the 0, but it's always 1. The second one, working from right to left, is a 2. And then I have 2 squared, 2 cubed, And if it continued, I've had 2 to the 4th, 2 to the 5th, 2 to the 6th, and so on. Powers of 2 are kind of nice because you probably know some of them. Does anybody know what 2 cubed is? 8. So this is actually 1 times 8. You don't have to write that part out that I'm about to do, but I want to make sure you're seeing it. This is 0 times 2 squared. What's 2 squared? 4. And then I have 0 times 2. I know that's 0, but I'm just going to leave it as 2, 0 times 2 right now. And 1 times 1. You got to have one of those 2 lines written down. If you jump from the question to what I'm about to write down as the answer, I'm going to assume that you might have looked at somebody else's paper, you looked at the back of the book, but the work between there shows me that you understand how the process works. So I want to see one of those 2 lines of work every time you do a problem like this, okay? Now, if I do add these up, what do I get? 9. Very exciting 9, which is much smaller than the smaller looking than the 4-digit number I started with, because there's only 1 digit. We're going to do that same T00 that we saw before. Now, I'm going to write it that way for the moment, right? T times a parenthesis plus 0 times a parenthesis plus 0 times a parenthesis. And in filling in my parentheses on the right-hand side, we always start with 1. What base is this in? 12. So then I've got 12, and what would the next one be? 12 squared. Please don't tell me that the answer is 144t. That's what it looks like right now, right? The zeros at the end cancel out. This is 144t. T has a value. What is its value that we're actually thinking of? It's 10. So it's actually 10 times 144 plus 0 times 12 and 0 times 1. And 10 times 144 would be 1,440. Now, if you want, you can write the word 10 beside it. You don't have to. But if it's not a 10 that you're trying to say it is, you have to write it, because the assumption is going to be that you're working in base 10 unless you say otherwise. Okay? Now, I want you to notice something that's very interesting here. This is a 4-digit number in base 2, and it's a 1-digit number in base 10. This is a 3-digit number in base 12, and it's a 4-digit number in base 10. What do you conjecture is going on in terms of the length of the number and the size of the base? What does it look like happened? There are fewer, let me say it again the way you just said it. There's less value with a smaller base. So what do you mean by less value?
There's less value in a bigger number.
Okay, so I'm trying to figure out if you're saying what I think you're saying, and I'm not 100% sure. So hold tight to a second. If we can have another interpretation, maybe you can be like, yeah, that's what I meant. Do you have another thought, Erica?
If the base is smaller, the amount's going to be longer, like the number's going to be longer.
That's how I usually think about it, and maybe that's what you're trying to tell me, Emily. If your base is smaller, then you've got more numbers that you have to write down.
Yeah, that's what I
Okay, good. I was thinking that's probably what you meant, but I wasn't quite sure with your language. So, yeah, so a smaller base, this is base 2, and I had 4 numerals, right? And this is base 10 over here, and I had 1 numeral. Bigger base, fewer numerals. And the same thing happens down here, right? Base 12, and I have 3 numerals. And once I have base 10, which is a smaller base, I have 4 numerals. Generally speaking, going to happen, okay? There might be some very random cases where the number of numerals stayed the same. It'd have to be a number that was pretty close to a base 10 number to start with for that to happen, just FYI. But otherwise, you're looking at that happening all the time, okay? And that should sort of make sense. I have to have more numerals because I have fewer numerals to pick from, right? How many numerals do I have in base 2? 2. right? I mean, I run out of options really fast. I have to get 2-digit, 3-digit, 4-digit numbers before I'm ready for them, maybe even because I just don't have anything else to write down, right? I'm out of options. And so I have to actually repeat things more quickly and have a longer value in terms of how many values are written there. All right, the next thing we're going to do is to convert the other direction. We're going to go from base 10, our base that we know and love, back into base whatever else we're looking at. So in this case, on the first one, it's base 4 that we're going to do. So here's how we do this. We consider the expanded form for the base. Now, the reality is I've already shown you how to do this. We did it for the Babylonians and we did it for the Mayans. We turned one of our numbers into a Mayan number, one of our numbers into a Babylonian number. Well, we ran into all sorts of problems. We don't have the problems here, okay? But we did this. We're going to do the same process. So we consider the expanded form. What does that mean? Well, it means what powers am I looking at? Is it base 4? Well, then I need powers of 4. Is it base 10? Or 12? I need powers of 12, and so forth. And then we use a division scaffolding. And that's what I showed you last time, was division scaffolding. So we're going to do a base 4 example so you can see how it works again. So 1 is our first value and 4 is our second one. What is 4 squared? 16. And then 4 cubed? Don't everybody answer at once? It's 64. How about 4 to the 4th? 256 is correct. 4 to the 5th.
1024.
Okay, so I'm going to keep going, but does anybody know how far I'm going to have to go? How will I know when I'm done? Say it louder, Cassie.
Close to that number.
Yeah, I need it to be close, or at least not to go more than this number. And I'm not there yet. So 4 to the 6th is what?
4096.
4096, which is getting really close. And how about the 4 to the 7th?
384.
All right, so it's 16,384, and that is too big. Agreed? Okay, so I don't need this one. I need all the ones before, though. So I have 1, 2, 3, 4, 5, and then here was a 4 and 1, 6, 7. There's 7 values. And I have to divide by all 7 values in this process. Don't go skipping anything. You're going to miss a number. So how does it work? Well, the biggest one goes first, 4096. And we do that top hat. Remember that top hat from last time? 11028. And we divide. How many whole number times does the number 4096 go into 11,028? So 2. What is 2 times 4096?
8,192.
Thank you, 8,192. And I subtract, giving me
2,836.
nice. And then I can continue my top hat, the division scaffolding down. I'll divide by the next value. What will be the next value I divide by? 1,024, which will go in how many times? 2. I don't know about you, but that one's small enough I can do in my head. 2,048. What's the subtraction for that?
788.
Right. What's the next value I would divide by? 256. How many times will it go into 788? 3. And what is 3 times 256? 768. Good job. And if I subtract, what do I get? 20. Nice. What would I divide by next? 64. I'm so glad you guys said that. I know the answer is going to go in 0 times here, but I still need that 0. The 0 as a placeholder is important. We saw what happened when we didn't have 0 placeholders, right? It was not good. So I've got 0 going from down here. I'm subtracting, and I still have a 20 left. After the 64, I have 16. So how many times will the 16 go in? Did I skip something? No. Oh, I know what I did. I just rewrote something funny on my paper. You're fine. Goes in one time, thank you. That's 16. And then I have a 4. And how many, what will I divide by next? 4, and that gives me a 1. And so you might be tempted right here to stop because you got 0, but we still have to divide one more time by the 1. Of course, that's going to give me 0. But again, the 0 is a placeholder. So the cool thing that I like about division scaffolding, and there are other books that show you other ways to do this, so I'm not sort of like clueless to the fact that this is not my only option. But I like this option a lot because the answer is right there on the right-hand side. All those numbers in order, top to bottom, are the answer. So the answer is 2, 2, 3, 0, 1, 1, 0, and it's base 4. And take a look. I started at base 10, I changed it into base 4, and I ended up with more numerals. Smaller base, more numerals. Okay, we're going to do the last one super fast. You guys ready? Okay, I'm going to give you the values as we go. Just trust me that they're all there. My powers of 9 are 1, 9, 81. I know you can do all of those. 9 cubed is 729. 9 to the 4th is 65, 61. And 9 to the 5th is 59,049. 59,000 is already very close to 99,000. In fact, it only goes in once, so I'm not even going to write the next one down. So 59,049 will go into 99,999 one time. The remainder is still quite large. It's 40,950. I will divide by what? 6561, and it actually goes in 6 times. 6 times 6561 is actually 39,366. We can subtract those, and we actually get 1584. I'll divide by 729, and that would go in twice for 1458. That remainder is a 126. All right, 126. Our next value to divide by is 81. That's just going to go in one time. So I subtract an 81, I have 45, which I would divide by 9, because my next power down goes in 5 times. And I get 0. Am I done? No. How do you know when you're done? When you divide by 1. That's right. Dividing by 1 at the end. This means there isn't anything else to divide. It's a 0 at the end, but a 0 placeholder. So the answer ends up being 162,150. Base what? 9. And again, take a look. How many numerals do I have in base 9? 6, right? How many numerals did I have in base 10 up there at the beginning? 5. Smaller base, more numerals.